Hi, my name is Jacob Taclay. I'm a senior at HBU and majoring in electrical engineering.
And my name is Richville Fagaragan. I'm also a senior at HPU for the electrical engineering program.
Our advisor is Dr. Sikati Naik, and acknowledgements to Prisa Anod for the building of this project. Our project revolves around the designing and building of a wireless charging system for model cars. Wireless power transfer, or abbreviated as WPT, can be often defined as the transmitting of power, electrical energy from one point to another without the use of any physical wires. Um, in the case of smartphones, the integration of wireless charging technology today is becoming more of a widespread feature. As for electric vehicles gaining popularity in the world, it's important to note that the majority of EV charging stations currently rely on wired connections for power transfer. Objectives and purposes so within the 1 year design and development project, our initial objective was to interpret the mechanism and practice of wireless power transfer systems. Moving forward is we have the purpose to lay out and construct our own system while utilizing proven circuit compositions and structures. Um, and in the end, our goal for our system is to charge or recharge the battery of a remote control RC battery, implementing and displaying the concept of wireless power transfer. So for this project, we researched wireless power transfer. This gives us the opportunity to create a block diagram to help us understand. In the future slides, we will be providing a brief description of each component, detailing its function and its fit to the overall circuit.
All right, so the first circuit design we'll be focusing on is the DC to DC converter because AC mains and DC power supply are common technologies. They are existing technologies. So it's basically a power supply plug. So for our DC to DC converter, we decided to use the same converter because in the high frequency AC inverter section, and the load it runs on an output of 5 volts or similar to 5 volts. So our chip we based it off of the Texas Instrument LM2596 LM2596 DC converter. It basically takes a supply voltage of 4.5 volts to 40 volts and steps it down to 3.3 volts or 5 volts or 12 volts or adjustable based on the user. So our design focuses on having it have an input of 12 volts and output of 5 volts with a maximum current of 3 amps. So we basically followed the data sheet that was provided by Texas Instrument. This is the top right shows their fundamental circuit design, and we're uh, using their tables and their procedure for creating the circuit. We have the one on the bottom right. The next one is on the transmitter side, which is the H bridge. So we need to. There are 3 components to form an H bridge, and the H bridge is basically got its name because it forms an H from the following components. So we need a PWM generator that produces a square wave, an H bridge driver that allows the MOSFET allows these switches to turn on and off, and the switches itself is a power MOSFET. So we want the PWM generator to produce a 100 kilohertz signal, which a PWM is basically a square wave that is able to drive the switches and has such allows the coils to resonate at 100 kilohertz. Our design output voltage is 12 volts. And this is our general schematic of entire transmitter circuit. And then this is for the receiving side, which converts the AC from the transmitter coils and the transmitter circuit to DC, which is, and in this case, we use the basic 4 diodes approach.
Sorry, for the circuit design and for the power management IC, uh, the circuit we used was revolving around Texas Instrument BQ2954PN's IC chip. The role of this circuit design is responsible for controlling, adjusting, and distributing power to a specific load. The iChip itself is designed for charge and power management of lithium-ion batteries, featuring built-in switching capabilities. Uh, Areas around the IC chip also include the LED indications, voltage and current regulators. The circuit has a rating max current flow of 1 ampere. The following circuit we're going to use also implements the removal of temperature sensing, uh, uh, the temperature sensing feature. By this, we're configuring the resistor values of resistors 11 and 12 within the schematic.
And before we build the actual circuit physically, we got to simulate it in software. So we use Multisim, which is a software made by National Instruments. So this is for the DC to DC converter. As you can see, it produces a flat 5-volt line. For the pulse width generator from the output of the 555 timer, we can see it produces a square wave with an output of 5 volts, which will eventually be fed to a driver, which is an output of 12 volts. And then if we integrate all of it, including the coils and the rectifier, along with the transmitter circuit, we can see that it produces 12-volt DC simulated. And after simulation, we build it on a proto board, which basically means we have to solder, which is basically a printed circuit board that all the components and the wiring has to be made by the user.
The implementation of the power management integrated circuit, or PMIC, on the breadboard proved to be challenging and extensive. Overall, afterwards, the assembly proved that the battery was not being able to be charged, as well to be non-functional.
So the issues with the proto board of the wireless transmitter circuit is that it actually, due to the wiring it causes the power MOSFETs to overheat, which means the circuit cannot sustain for a long duration of time, which means it will fail, and as a result, voltage will drop at the output.
And in summary, with the breadboard for the PMIC, of course, that the lithium batteries was not charging, as well as there was no indications of the LEDs lighting up, determining whether the battery was being charged or fully charged.
So we basically go with letting a company build the PCB for us. We use EasyEDA as the circuits designer, PCB designer, and we export it to the company of JLC PCB. So the first version did not include the bypass caps or made the trace width very big. As a result, one of the traces burnt, as you can see it over here, which means the first version did not work as well. However, the second version did work because we made the trace width bigger and we included bypass caps.
So since that the breadboard fabrication of the PMIC did not work, we decided to give the opportunity of PCB fabrication of the PMIC. The picture describes that the image done in EasyEDA, so that we can fabricate into a PCB format. So after sending our schematic design and fabricating the PCB, on the left is the initial package that was delivered, and on the right is the finished product of all the soldered components. on the circuit board PCB so that it can help it operate and be functional.
We also PCB fabricate DC to DC converter and full bridge rectifier. And this is our test without the power management IC. And the rectifier is able to output about 10 volts, which is 2 volts off from the simulated version.
Here we have the testing of the PCB power management IC. On the left, it indicates that the LED light of the red LED light was turning on, indicating that the battery was being charged, but not fully charged. We have two pictures of the power supply showing different input voltages, one being at 8.5 and the other one being at 9.1. The 8.5 input voltage shows 0.44 current draw, as the 9.1 shows a 0.55 current draw. The multimeter, next picture of the multimeter shows it in series with the battery and the PCB, and it shows that a max current of 0.441 amps is going into the battery. For this design, we made two implications of the PCB. This is the second one. The second one proved to be faulty and non-functional because of the LED lights not lighting up. Another indication shows that while rising the input voltage, the current draw remained at 0.1 or less. And then after results of increasing the input voltage, one of the capacitors blew, making it unstable and non-functional.
And this is the integrating all of it with the PCB power management board to charge a regular lithium battery, which is the typical cylinder cell. And after 10 minutes, it only charges the battery at 0.007 volts, which is very slow. And we are attempting to integrate it with the remote control, but we didn't have time to fully test it as of the making of this video. So we just plopped the transmitter coil on the receiver coil on the RC car, transmitter coil on a platform with the box representing which contains the transmitter circuit itself. And for the fabrication of the transmitter circuit itself, using EasyEDA, it removes the problems that I had with the photo board. And for the PMIC, we were able to recharge the battery and have the LED to be on, which is a benefit, which is a huge benefit, a huge plus over the breadboard. The next steps would be improving the coils, increasing the speed of charging, add a PMIC to the transmitter circuit, make the entire system overall better with better controls using a microcontroller, and ultimately make the RC car charge on its own. Thank you.
Thank you.